August 2nd, 1941, Detroit, Michigan, the Packard Motor Car Company test facility. 2 Rolls-Royce Merlin engines roared to life on test stands, their 12 cylinders producing a sound that would change the course of World War II. But these weren't British engines. They were American, built in Detroit, by a car company, from British blueprints that had taken decades to perfect. 14,000 individual parts, each one traditionally hand-fitted by skilled British craftsmen who'd spent years learning how to feel when tolerances were right. Packard had 11 months to figure out how to mass-produce these engines on assembly lines, with workers who'd never built aircraft engines using American tooling and measurements without losing a single horsepower of performance. The British thought it was impossible. Packard's lead engineer looked at the Rolls-Royce blueprints and said something that offended every British engineer who heard it. "Your tolerances are too loose." What happened next was a clash of engineering philosophies that would determine whether Allied bombers could survive over Germany. And it all started because American pilots were dying at 30,000 feet. The P-51 Mustang was beautiful, fast, and deadly. At low altitude, below 15,000 feet, it dominated everything the Germans could throw at it. The Allison P-1710 engine was powerful, reliable, and perfect for the role North American aviation designed it for. But there was a problem. American bomber formations were flying missions at 30,000 feet and above. At those altitudes, they needed fighter escorts. The P-51 with its Allison engine couldn't get there. The single-stage supercharger on the Allison just couldn't compress enough air at high altitude to maintain power. Above 15,000 feet, the Mustang's performance fell off dramatically. Above 25,000 feet, it was a sitting duck, and American bomber crews were dying because they had no fighter protection over German targets. The Luftwaffe learned to wait until escorts had to turn back due to limited range, then they'd attack the undefended bombers. Losses were catastrophic. Something had to change. The British had a solution. The Rolls-Royce Merlin engine powered the Spitfire to altitudes above 30,000 feet with power to spare. Stanley Hooker's 2-stage, 2-speed supercharger was the key. It compressed air in 2 stages, dramatically improving high-altitude performance. It was exactly what the P-51 needed. But there was a problem. Rolls-Royce was producing about 200 Merlin engines per month. Every one of them was needed for British aircraft. America needed thousands, quickly. The solution seemed straightforward: license the Merlin design to an American manufacturer and produce it domestically. In practice, it was anything but straightforward. Packard Motor Car Company won the contract, $130 million to produce Rolls-Royce Merlin engines in Detroit. Packard made luxury automobiles. They had never built an aircraft engine. They had never worked with the British. They had never dealt with the unique challenges of adapting a hand-built engine designed for artisan production to American mass manufacturing. The British sent over the blueprints with the confidence of people who knew they'd created the finest aircraft engine in the world. What they sent was, to American eyes, barely adequate as documentation. The drawings showed what the final product should look like. They didn't show how to make it, because Rolls-Royce didn't make engines on assembly lines. They built them. Each engine was assembled by skilled craftsmen who fitted parts by hand, filing and adjusting until everything was perfect. The tolerances on the drawings were loose because the final precision came from the fitter's skill, not from the manufacturing process. Packard's chief engineer, a man named Jesse Vincent, examined the British specifications and made his assessment. The British build engines like Swiss watchmakers. Every part is fitted individually. We need to build them like Ford builds cars. Every part perfectly interchangeable. The British were offended. They'd been building Merlins for years. These engines powered the Spitfires that won the Battle of Britain. The supercharger technology was the finest in the world, and now some American car engineer was saying their tolerances were inadequate. Vincent wasn't criticizing British engineering. He was pointing out a fundamental difference in manufacturing philosophy. British approach. Build each engine as a unique creation, fitted by skilled craftsmen to exacting standards. American approach. Create manufacturing processes so precise that every part is identical and interchangeable without hand-fitting. Both approaches could produce excellent engines, but only one could produce 400 engines per week. The challenge facing Packard was enormous. Take 14,000 parts designed for hand assembly and re-engineer them for mass production. Maintain exact performance specifications. Change nothing that would reduce power, reliability, or durability. And do it in 11 months because pilots were dying and the war wasn't waiting. What followed was one of the most intensive engineering efforts of the entire war, and it started with something as simple and as complicated as screw threads. The British used Whitworth standard threads. America used Unified Thread Standard. They're both called imperial measurements, but they're not compatible. A British 1/4-inch bolt won't thread into an American 1/4-inch nut. The thread pitch is different. The thread angle is different. Every single fastener in the Merlin engine used British standards. Thousands of bolts, nuts, studs, and threaded holes. Packard had two options: import British fasteners and tools, creating a supply chain nightmare, or manufacture British standard threads in America to tolerances tighter than the British used, ensuring perfect interchangeability. They chose option 2. Packard tooling engineers created custom tooling to manufacture Whitworth threads. But they didn't just copy British manufacturing methods. They applied American precision engineering. The result was British standard threads manufactured to tolerances the British themselves didn't achieve. When Rolls-Royce engineers tested Packard-made parts, they were shocked. The American parts were more precisely made than British parts. A Packard bolt would thread perfectly into a Rolls-Royce engine. A British bolt would thread into a Packard engine. Complete interchangeability, something the British hand-fitting approach had never required or achieved. This wasn't just about fasteners. It was a preview of Packard's entire approach. Understand the British intent, then exceed British execution through American manufacturing precision. The metallurgy presented another challenge. British bearing materials were copper-lead alloys, traditional and proven. Packard engineers analysed the loads and operating conditions and determined they could do better. They substituted silver-lead bearings with indium plating, higher load capacity, better wear characteristics, longer service life. Rolls-Royce tested the American bearings and grudgingly admitted they were superior to the original specification. The supercharger impellers were perhaps the most challenging component to manufacture. These aluminum wheels spun at over 30,000 RPM, compressing air to feed the engine. They had to be perfectly balanced. Any imbalance at those speeds would destroy the engine. The British balanced impellers through iterative hand adjustment. A craftsman would spin the impeller, feel for vibration, remove tiny amounts of material, test again, repeat until perfect. It worked, but required hours per impeller and depended on craftsman skill. Packard developed dynamic balancing equipment that tested impellers at operating speed. Precision casting techniques reduced the amount of hand finishing required. The result was impellers that met British balance specifications but could be produced in minutes rather than hours. Same performance. Radically different manufacturing method. This pattern repeated across every component: British design, American manufacturing engineering. The combination produced engines that were identical to Rolls-Royce Merlins in performance, but superior in manufacturing consistency. Over 11 months, Packard engineers created 6,000 new technical drawings, not copies of British drawings translated to American units, new drawings that captured the design intent while specifying American manufacturing processes. Every tolerance was recalculated. Every material was analysed and often improved. Every manufacturing step was engineered for assembly line production. The British watched this process with a mixture of scepticism and growing respect. Packard wasn't just copying the Merlin. They were re-engineering it from the inside out, maintaining performance specifications absolutely, but changing everything about how it was made. The test on August 2nd, 1941, was the proof of concept. The two engines had been assembled entirely from American-made parts, nothing hand-fitted, everything straight from the assembly line. If the engines ran, if they produced rated power, if they met all performance specifications, then Packard's approach worked. Both engines started on the first try. Both ran smoothly. Both produced full-rated horsepower. British observers took detailed measurements and compared them to Rolls-Royce specifications. The American engines met or exceeded every requirement. Vincent's assessment had been proven correct. The British tolerances weren't wrong, they were just designed for a different manufacturing philosophy. Packard's tighter tolerances and precision manufacturing produced engines that were consistent, interchangeable, and ready for mass production. By 1943, the Packard plant in Detroit was producing 400 Merlin engines per week. 400 every week. The entire Rolls-Royce production in Britain was about 200 engines per week across all their facilities. One American factory was producing double the output of the entire British Merlin program. The engines went straight into P-51 Mustangs that were rolling off North American aviation assembly lines at unprecedented rates. The transformation of the P-51 from low-altitude fighter to high-altitude escort was complete. With the Packard Merlin, the P-51 could reach 41,900 feet. It could cruise at over 400 miles per hour. It had the range to escort bombers to Berlin and back. The impact on the air war over Europe was immediate and decisive. German fighters that had been slaughtering unescorted bombers suddenly faced P-51s at every altitude. The Mustang's performance with the Packard Merlin exceeded even the best German fighters. Luftwaffe pilots who dominated the skies found themselves outclassed. Allied bomber losses dropped dramatically. The strategic bombing campaign that was supposed to cripple German industry could finally proceed as planned, because Packard engineers had figured out how to mass-produce a hand-built British engine. The technical achievements were remarkable, but the cultural clash was equally fascinating. British engineering culture valued craftsmanship, individual skill, and artisan precision. Each Rolls-Royce Merlin was, in a sense, a unique creation. The fitters who assembled it took pride in their work, in their ability to make parts fit perfectly through skill and experience. American engineering culture valued process, repeatability, and scale. Each Packard Merlin was supposed to be identical to every other Packard Merlin. The fitters who assembled it followed procedures designed to eliminate the need for individual judgment. Neither approach was wrong. They were optimized for different objectives. British approach: maximize quality through skilled labor. American approach: maximize quantity through process engineering. The war required both. Rolls-Royce Merlins kept the RAF flying when British survival depended on it. Packard Merlins provided the volume needed to equip American air forces fighting a two-ocean war. The fusion of British design and American manufacturing was more than just pragmatic cooperation. It represented a genuine synthesis. Packard didn't just copy Rolls-Royce. They learned from British engineering and contributed American innovation. The bearing improvements, the precision casting, the dynamic balancing, these were American contributions that enhanced the British design. Rolls-Royce, for their part, learned from Packard's manufacturing methods. After the war, British engine production incorporated elements of American mass production philosophy. The distinction between hand-fitting and precision manufacturing blurred as both industries learned from each other. The Packard Merlin story is often told as American industrial might saving British innovation. That's oversimplified and slightly unfair to both sides. The truth is more nuanced. British engineering created one of the finest aircraft engines ever designed. The Merlin's performance, reliability, and elegant engineering were genuine achievements. But British manufacturing capacity couldn't produce engines at the scale required for global war. American manufacturing engineering took that British design and made it producible at industrial scale. Not by dumbing it down or accepting lower quality, but by re-engineering every aspect of production to achieve consistency through process rather than through individual craftsman skill. The combination was unbeatable: British innovation, American production. Together, they created the engine that powered Allied victory in the air war over Europe. The numbers tell the story. Packard produced over 55,000 Merlin engines during the war. Rolls-Royce produced over 150,000 across all variants. But Packard's contribution wasn't just the engines they built. It was proving that high-performance aircraft engines could be mass-produced without sacrificing quality. The legacy extends far beyond World War II. The manufacturing techniques Packard developed for the Merlin influenced post-war aerospace production worldwide. Statistical process control, precision casting, dedicated tooling for complex threads. These became standard practices in aircraft engine manufacturing. The bearing technology Packard developed found its way into automotive applications. High-performance engines in the 1950s and 1960s American cars used bearing designs descended from Packard's Merlin work. The international standards for thread compatibility and interchangeability were influenced by the lessons learned from the Merlin program. Engineers realized that global cooperation required standardization that went beyond simple measurement conversion. Today, the few airworthy Merlin engines still flying are treasured artifacts. Many are Packard Merlins. 75 years after manufacture, they still run smoothly, still produce rated power, still demonstrate the excellence of 1940s engineering. When you hear a P-51 Mustang at an air show, that distinctive sound is often a Packard Merlin. American-made, British-designed, representing a moment when two different engineering cultures combined to solve an impossible problem. The engines work as well today as they did in 1943. That's not accident, that's engineering. The story has a human dimension beyond the technical achievements. The Packard workers who built these engines were largely women. The war had taken male workers into military service. The assembly lines were staffed by women who'd never worked in manufacturing before. They were trained in precision assembly techniques, taught to read complex blueprints, and expected to maintain quality standards that exceeded anything in automotive production. They succeeded. The rejection rate for Packard Merlins was lower than for automotive engines. First-run acceptance was higher. These weren't experienced craftsmen with years of training. They were ordinary people, mostly women, following precisely engineered processes that eliminated the need for years of experience. That's the power of process engineering. Create systems good enough that ordinary people can produce extraordinary results. The British craftsmen building Merlins at Rolls-Royce were skilled professionals with years of training. The American workers building Merlins at Packard were trained in weeks. Both produced excellent engines. The difference was scalability. You can't train 10,000 craftsmen in a year. You can train 10,000 assembly workers to follow precise processes in a matter of weeks. The initial British skepticism about American manufacturing capabilities was understandable. From their perspective, Americans were automobile manufacturers trying to build precision aircraft engines. The gap between building cars and building high-performance aircraft engines is enormous. Cars operate at relatively low speeds and temperatures. Aircraft engines operate at extremes. Cars are designed for tens of thousands of miles of service. Aircraft engines need to perform flawlessly for hundreds of hours under combat conditions. The engineering standards are completely different. Packard proved that automotive manufacturing expertise was transferable, not directly, not without modification, but the fundamental principles of mass production, precision machining, process control, and quality assurance applied to aircraft engines just as they applied to automobiles. The key was respecting the engineering intent of the original design while reimagining the manufacturing process. That respect was crucial. If Packard had simply tried to build Merlins cheaper and faster by cutting corners, they'd have failed. Instead, they often exceeded British specifications. The tolerances were tighter, the materials were better, the processes were more controlled. They proved you could mass-produce quality. That was the American contribution to the partnership. The $130 million Packard spent on the Merlin program was enormous by 1940s standards. In modern terms, adjusted for inflation, it's over $2 billion. That investment bought more than engines. It bought a manufacturing capability that transformed American aerospace production. The techniques developed for the Merlin were applied to other aircraft engines, to jet engines after the war, and eventually to space program hardware. The institutional knowledge created at Packard spread throughout American industry. Engineers who worked on the Merlin program went on to other companies, other projects, carrying lessons learned with them. The ripple effects lasted decades. The Rolls-Royce perspective